Okay, guys. So this course is mainly about amplitude modulation and frequency modulation techniques, and there is one more thing, which is how do they perform under noise, and that will be towards the end. And this is probably one of the first abstract course you are taking. We will not be really dealing with any electronics, but everything will be mathematics, and it's a lot of trigonometric identities and Fourier transform. So if any weakness you have on Fourier transform is going to really affect you. Okay, so the tutorial questions and my lecture notes will have a lot of Fourier transform questions. Please make sure you understand all of them before the midterm, because there will be Fourier transforms involved in the midterm. Okay, so other than that, before I show you the other 2 points, the best way to understand what is going on, the abstract things that are going on in this course, is to first focus on amplitude modulation and to think of an AM station. Like if you are living in a city like city of Toronto, you probably don't have a radio at home, but definitely you will have a radio in your car or your family member's car, and people often listen to AM 680, which is 680 news, or 590 AM 590 sports, and so on. So think of, let's use 680 news as the example. So 680 actually means 680 kilohertz, and we will come to that what that exactly means. That's called the carrier frequency, but we will talk about carrier and the message signal in a moment. The best way to understand what is going on is to think about what happened like 30 years ago. Because there is a difference between what happened 30 years ago and now. So 30 years ago, even though there were digital computers and a lot of digital things, the AM and FM broadcasts and television broadcasts were not digital. So everything is analog. So let's first talk about that. So imagine in 680, someone is reading the news and the sound waves are converted to electrical signals by the microphone, and then those electrical signals, which the best way to imagine them is voltage versus time. But in this course, we are not going to think about the voltage, because it could be current. We don't care. The vertical axis has no unit. We will just leave them without the unit. But the horizontal axis has unit, which is the unit of time. So the electrical signals are then amplified. Maybe they did some filtering, but that's not important. Then they connected it to an, imagine someone connected to an antenna, the electrical signals. So the electrical signals, maybe you can think of amplifying to, let's say, 200 watts or even 1000 watts, and connecting it to an antenna. And then imagine the antenna is about 5 meters, 10 meters, or even like 75 meters long. So the antenna will radiate the electrical signals as electromagnetic waves, but the problem is those waves will only travel a few hundred meters. And so there is a course called Electromagnetics. I believe it is also a third-year course. If you take that course, you will quantitatively understand the efficiency of the conversion between the electrical power that reaches the antenna, what percentage of that power converted into electron energy of the electromagnetic wave. And that conversion efficiency depends on the antenna size, the power of the signal reaches the antenna, like how many watts, also on the frequency of the signal. And most importantly, so for example, first of all, if you want to broadcast over a city, then you will probably need like a 1 kilometer, 2 kilometer, 5 kilometer antenna. So with reasonable size antennas, you will not be able to transmit the signals over a city. You can't really increase the power for more than like 1000 hertz to 1000 watts or 2000 watts because it's not practical. So about more than 100 years ago, people came up with a brilliant idea. What they did, the engineers came up with an idea. What they did is, before connecting this amplified audio signal to the antenna, they did something interesting. They took a high frequency signals. For example, if you are using 680 news, it will be a 680 kilohertz pure sinusoid, a cosine wave. And they take that 680 kilohertz wave and modulate it with vary the amplitude of instantaneous amplitude of that cosine signal, amplitude of the signal in proportion to the instantaneous value of your audio signal. So when the audio signal will be like a smooth curve but random, and when the audio wave has a high amplitude, instantaneous amplitude, the amplitude of the cosine wave at 630 will be high. When audio wave height is less, the amplitude of the carrier wave that is transmitted will be less. When audio signal is less, this will be less. When audio signal has a high amplitude, the amplitude of the carrier signal will be higher. So I missed one point there. So the transmission efficiency depends on the frequency, but unfortunately, the maximum frequency in audio signals are 20 kilohertz. So that's why they didn't travel that fast. So by going to a frequency like 680 kilohertz, we are increasing the transmission efficiency. So lots of the power in this 2000 watts or something like that will be translated into power of the electromagnetic waves, so they will travel farther. So that is amplitude modulation. So I was talking about more than 100 years ago, and after amplitude modulation, about 10 or 15 years later, they came up with another technique. Take a cosine wave of frequency around 100 megahertz and change its frequency in proportion to the instantaneous amplitude of the audio signals, and that is called frequency modulation. So before the midterm, we are going to talk about amplitude modulation only, because in amplitude modulation there are 3 different techniques, and because of the accelerated format, we are only going to study 2 techniques. So let me first show you some diagrams about amplitude modulation. I have basically, now what happened in this last 30 years is they take the audio signal, amplify a little bit, and then convert it to a digital signal, do analog to digital conversion. But that digital signal is still a low frequency signals. For example, if your amplitude maximum frequency in the audio signal is 20 kilohertz, and then you can sample it and get a digital signal, and that the rectangular wave or square wave, if it is 20, will be like under like maybe 200 kilohertz or something like that, and it is still a low frequency signal in terms of the efficiency is concerned. So what they do nowadays is they use that digital signal to amplitude modulate a carrier. So that's the first diagram I am going to show you. So also in this first lecture you have to begin to understand the terminology. So we'll be talking about a baseband signal or message signal. I introduced this baseband, the word baseband, because we will be using this, you will be using this again often when you study this digital stuff here. Not in this course, in a fourth year course called digital communications. There you will hear the word baseband signal often. But in this course, I will stick to message signal, which is more straightforward. So message signal, the best way to think about message signal, even though I have a digital diagram here, I'll go a little bit further as the signal coming from the microphone after a little bit of amplification. So this is the analog message signal, baseband signal, and here you have the carrier, a high frequency sinusoid, and its amplitude is varied in proportion to the message signal. So you can see this variation in the instantaneous amplitude of the audio signal is tracked here. The amplitude look exactly like this shape, and the same shape here is inverted. So this is what happened like until before 30 years ago. After that, what they did is the analog audio signal is converted to a digital signal, and the digital signal is now digital signal modulates the carrier. And there are many ways to use a digital signal to modulate the carrier. The simplest one is called on-off keying, and it looks like this, because here the amplitude is 0 if you notice. So all of the height becomes 0. Now, having said this, in the fourth year digital communication course, you will learn a lot more. For example, after taking the microphone signal and amplifying and converting into a digital signal, they add, so it will be all bits, zeros and ones, but we actually add more zeros and ones, which is called the source coding. Some of you may have heard about error correction codes, but what actually happens is a little bit more complicated than error correction codes, but that's the basic idea. And then we modulate it, and then we add some more bits. So there is a lot of digital things going on, but we won't worry about, we are not going to worry about those things. Those things are studied separately in the digital communication course. Okay, so the best way to understand what happens in this course is whether this is a digital signal or an analog signal. It doesn't really make like any difference to the math we are going to use. Very often we will draw diagrams like this, or we can think like this. Sometimes we may have to think of them like this, but the math is the same. Okay, so if you really want to have a concrete example of what is happening, think about the 680 news. Somebody speaking in the microphone, and the electrical signals are amplified, and they modify the amplitude of a high frequency carrier. Right? Okay. That's a long introduction, and all of that is basically here. So now there are other use of amplitude modulation which you must be aware of. One is called multiplexing. This is very important. For example, what is happening over the air is actually multiplexing, because through the same air over Toronto, you have 680 news coming to your house or a car, 590 sports is coming, talk radio 1010 is coming. So a lot of signals are coming, and they are not really interfering with anything. You can clearly hear each audio signal separately. By the way, one more thing I forgot to mention here is So this is the transmitted modulated carrier. This comes to your car or home, and then from this signal you have to recover the audio signal back or the message signal back. So that is what radio receivers do. That is called demodulation. So in this course we are going to talk about modulation and demodulation. Okay, and the modulation circuit and demodulation circuit, and then we are also going to do a lot of math. So in multiplexing, in radio broadcast, multiplexing is already happening, but the best way to understand is think of a coaxial cable. Coaxial cable is like if you have Rogers TV, then your TV signal is coming through a cable. If you have Bell TV, it's most probably a fiber cable. So let's not talk about it now. Coaxial is enough. The Rogers cable. Okay, so if you take a cable like that, imagine you have 5 different voice signal in your room or in your apartment or house. Okay, I'm not talking about a radio station. Let us say you are playing 5 different CDs in 5 different stereo. You can take those signals, put those RCA plugs in, and then there is a way to send all 5 signals through the same coaxial cable to another room or next house, and they can listen to those 5 different audio signals or CD, whatever the music, without any problems with the signals getting mixed up. So if you just add those 5 different audio signals and send it through the coaxial cable, at the other end they will all mixed up. You will hear the 5 songs at the same time. You won't be able to make any sense of it. But in multiplexing, what we do is we modulate, we take 5 different high frequencies. Maybe you can take one at 500 kilohertz, another one at 600, another 700, 800, and so on. And take the 500 kilohertz and modulate that, amplitude modulate that using the audio signal from the first CD. Take the 600 kilohertz cosine wave, modulate it with the second audio signal from the second CD. So now you have 5 different signals like this, modulated signal. You can add them and send them through the coaxial cable. At the other end, you can demodulate them. You will have 5 different demodulating circuits. Each will modulate the signal at, one will modulate the signal at 500 kilohertz, the other one at 600 kilohertz, so on. And you will be able to successfully recover the 5 audio signals. So that is called multiplexing. So that is one important application of modulation. Another application is, if anyone of you is interested in music, electronic keyboards, when they generate those fancy sounds, but they often take cosine wave and then do certain things to the cosine wave, but then they also employ modulation. So if you are interested in, you can read about that on the internet. There are some interesting blogs written by people who work at companies like Roland and Borg, which make world famous synthesizers and keyboards. All right. So the first 2 lectures are going to be review of signals and systems, because I already told you other than this introduction, you are going to use a lot of Fourier transform. So there is going to be a lot of review, and only the next 2 lectures will be actually about amplitude modulation. But let me emphasize again that the Fourier transform stuff is very important. Okay guys, one thing I forgot to tell you is always feel free to interrupt me and ask me questions. So any questions so far in this lengthy introduction? You guys are okay? Are you guys still there? Okay, thank you. All right. So the first thing we need to understand is I have to give you two different measures of the strength of the signal, because we may be using this at the end of the course. In order to motivate those definition, I'm going back to your actually like an electronic course. So I told you that in this, generally speaking, we are not going to talk about voltages or currents, but here I have a motivating example. So in this example, this voltage, time varying voltage, is applied across an 8 ohm resistor starting from t is equal to 0. So here it decays because it is e to the negative t over 3. The question says find the total energy dissipated in the resistor. So you guys know from the electricity course, the power dissipated in the resistor is V square over R, I square R or VI. We don't have the current here, so we will use V square over R. But that is the power. When we integrate the power, we get the energy. So the answer is going to be an integral P dt, where P is V square over R. Okay, Pt dt and V square over R dt. So then I squared this, and the only important thing is when you square this, a to the n squared, a to the n to the m is a to the nm. So the powers get multiplied. So when you square, it becomes minus 2t over 3. Now, and this integral is very easy because the antiderivative is very easy. And you should learn to integrate very fast. Where the idea here is the derivative of e to the x is e to the x itself. So you know that you can guess the antiderivative is what I have here. It is the same thing, but when you differentiate it, you will go e to the minus 2t over 3 multiplied by the derivative of the exponent, which is minus 2 over 3, and that minus 2 over 3 is not here. So we compensate it by multiplying by the reciprocal. Okay. Please don't be one of those people who make a substitution u is equal to this, because this looks complicated. No, you are in third year. Even in the first year calculus course, they should have told you when they start teaching you integration, they should tell you to quickly integrate this. This is called integration by inspection. Okay, practice this because it may come again towards the end of the course with even more complicated functions. Okay, this is just guessing. Whose derivative could this be? I pulled out 25 over 8 and guess the antiderivative of this. I know there is a problem because of the derivative of this. I compensated this, and in this case the signal never really becomes 0, so it is from 0 to infinity. Now whenever we have a signal that decays, we will use power as our measure because the power will be finite. Because when we talk about the strength of the signals, we don't want to talk about infinity. That's why when a signal decays, it's okay to use power. In the next example, we will have a periodic signal. When you have a periodic signal, we will talk about energy, because if you calculate the power from 0 to infinity, it is going to be infinity. So depending on how the signal looks like, we will be using either energy or power as our measure. Because this is decaying, it's okay to use the energy. And then we plug 0 and infinity and we get this. Motivated by this example, we define energy of a signal as this. So in this course, the signals will not be denoted by V of t or I of t, rather x of t or g of t. Meaning, we don't care whether it is current or voltage. And also, we take the assumption, we calculate the energy assuming the resistance is 1 ohm. Okay, so there is no R in this formula. This is very important. Okay, we assume the resistance is. What would be the energy if there were a 1 ohm resistor? So this formula is very important. Okay. Now here is another example where we have a periodic signal. So in this case, okay, the details are here, but this example is again a practical example. I calculate the power. You can verify how this is done when you have time. Motivated by this example. So look at the question. The way I did this is, I didn't integrate from 0 to infinity. I took one period from 0 to 7. See here, 0 to 7. Calculated the total power in that period and then took the average of that. Okay. So motivated by this example, we have this formula when we want to calculate the power of a signal. Okay. So I think I may have used, so this is the energy and this is the power. I am not sure if I switch the word. So please remember, there is, when you have a periodic signal, the appropriate strength measure is power, and what we do is we calculate the power over a period and divide by the value of that period. Okay. All right. So once again, I already mentioned this. We talk about signal again and again. What is a signal? Signal is any function of time. We are not going to bother with whether it is voltage or current. Okay, these are the trigonometric identities that are going to kill you if you don't master them quickly. Okay, so cosine A plus B is cosine A times cos A cos B sin A sin B, and then from this, if you put A is equal to B, you will get cos 2A is 2 you will get a formula for, it will become cos square A plus sin square A, but then for sin square A you can write 1 minus cos square A, and you can get the cos double angle formula, which is cos 2x is 1 minus, oh sorry, this is 1 minus, okay, cos 2x minus 1, cos square x minus 1, and from that you can isolate cos square x, and you have this formula. So this is the other formula that is very important. Okay, this came from cosine double angle formula. It's maybe worthwhile for you guys to derive this formula from this by putting A is x and B is x, and then using sine square is equal to 1 minus cos square x, and then isolating for cos square x. So we need a formula for cos A. Oh, by the way, from this we can also write a formula for cosine A, cos of A minus B. Then you can add those two equations. Some things will cancel, and you can derive this formula. Cosine A cosine B is half of cos A plus B plus cosine of A minus B. So basically, these two formulas, the second one here and this one, are the most important one. Cosine A, cosine B, and what happens with cos square x, cos square A, the same thing, right? So as an exercise, I suggest you guys integrate this, because to integrate the products, look at this example. Usually we use this formula, so it becomes half cosine of addition of the angle, which is 4x, subtraction of the angle, which is negative 2x, but cosine of negative x is the same as cosine of plus x. So this and this are the same. And then something very important is happening here. Let me explain. Imagine there is cosine x instead of 4x. Cosine x or sine x integrated between 0 and 2 pi is 0, because there is equal amount of area over the horizontal axis and under the horizontal axis, so they cancel each other. So cosine x or sine x over one period has equal area above the axis and below the axis. The area below the axis, if you remember from first year, is negative. That negative cancels with the top. So if this is x, cosine x, the answer is 0. But here it is 4x. The cosine 4x has a higher frequency. So cosine x goes up and down once or something like that, but this will go down, up and down even more. But the same cancellation will happen regardless of what number you have here. If this is a fraction, and if this is from 0 to 2 pi, like cos half x, then you have to be careful. Then you can think whether this is a fraction, and you can draw a diagram and figure it out. Or you can actually integrate and get the answer. But if this is an integer multiple, and if this is one full period, the answer is definitely 0. Okay? And you may want to use that later on. Alright. Now I am going to briefly talk about where this Fourier transform business came. I don't think you heard about some of these business in signals and systems. If you understand this, some of the Fourier transform formulas will become very easy, but I don't want to spend too much time on it. So first of all, the vector space R2 means vectors with 2 elements. I am sure you guys have heard about this. R3 means there are 3 elements, and then the dot product is defined as length A, length B, cosine theta. Some of you call it magnitude, but length is a better word. Length A, length B, cos theta. But the dot product can also be calculated just by multiplying the corresponding elements. Now, here is something, this is very important. If you take the dot product of the vector with itself, A dot A is length A, cosine 0, and cosine 0 is 1, because the angle between A and A is 1. And if you rearrange this equation, you get A dot A is length A square. This is a very important equation. You shouldn't always be in a you shouldn't be in a position that you have to actually substitute here and then get this result. You have to memorize this result. V dot V is length V square. That's a big formula. And then from that you get this formula. Length of a vector is square root of the dot product with itself. And this is so important because this is what is actually the definition of the magnitude of a vector. You guys usually calculate the length by taking the square root of this square plus this square. That is a theorem that came after this. So if you take linear algebra 2, unfortunately engineers take only linear algebra 1. Linear algebra teaches you advanced linear algebra, and you will understand this is how magnitude of a vector is defined, square root of this one. The reason this is important is soon we are going to think of a signal as a vector. So again, if you go a little bit more deep into math, you will realize everything is a vector. Things that we thought are functions are actually vectors, and then it just keep on piling, and like no matter what you get in math, you can think of it as vector. So signals, when we want to analyze signals, like engineers found out like decades ago, it's much better to think of them as vectors. So at some point we'll be talking about magnitude of a vector, magnitude of a signal. How do you calculate the magnitude of a signal? This is different from that instantaneous amplitude. Okay, we take a dot product with itself and take the square root. Now that brings the question, how do you take the dot product of functions? Okay, so but before that, to tell you why thinking of things as vectors is very important, the correlation coefficient from statistics is actually the angle between two vectors. And what is the vectors? The data points. For example, in statistics you will have one data which is like 1.3, 3.4, and there is a sequence of numbers. There is another data which is another sequence of numbers but same numbers. And in statistics we want to see whether these two data are correlated. So we think of the data as vectors and take the dot product here, which is a1, b1, a2, b2, a3, and then divide it by square root of this. So in statistics courses they usually give you this formula without mentioning where this formula came from. It is actually the cosine of the angle between the two data, where you consider the data as vectors. Alright, so let's go further. Alright, so this is where this idea of considering the signals as vectors comes from. So in fact, in linear algebra you will learn any function, any set of function, as long as they have the same domain, you can create a vector space. So what is a vector space? A vector space is like R2 and R3. But you can't mix R2 with R3. For example, you cannot take the dot product of this with this. You can only take dot product inside a particular space. So you have R2, R3, R4 and so on. What you are learning now is, if you take all the functions that share the same domain, you can think of them as a vector space and take dot product and calculate their magnitude and so on, calculate the correlation coefficient and so on. So that brings us the important question. Now you know there are infinite number of continuous functions that can be defined in any given interval. So one is this, and sin t, even though you can go to any domain, but let's restrict it to this just for the sake. But how do you find the dot product of this function with this function? So dot product means if you look at here, you multiply and then add, right? You guys remember, multiply and add. So with continuous function, multiplication, we multiply and integrate. That's it. And this is how all the formulas in Fourier transform came from. They are all dot products. Okay, and I will explain that in a moment. Before that, magnitude of a signal is take the signal and dot product it with itself and then take the square root, because that's the definition of length of a vector in linear algebra. Okay, so please remember these formulas. Okay, these are very important. Now there are other examples of vector spaces, but let's skip that. So here is an example. Find the dot product of this signal with this signal over this. What this means is, think of them as vectors in this interval. So the significance of this is, when we integrate, we use them as the endpoint. So you multiply and integrate. That is the dot product. Okay, just take a moment to look at this and make sure you guys understand this. Oh, sorry. In this question, it is just the dot product of this signal with this signal. You multiply and integrate over the integral. And the next question, find the magnitude of this signal. So what I did is I first multiply this by itself. It's over at the same interval. Okay. And then I took the square root of it. Because magnitude is dot product with itself and square root. Next question, prove this signal or this function is perpendicular to this function. Orthogonal is just a fancy word for perpendicularity. But how do you prove vectors are perpendicular? You show the dot product is 0. How do you take the dot product? You multiply and integrate. And I multiplied and integrated and showed it is 0. Okay. All right. Any questions so far? So when you take basically what happens is there is a bunch of definitions from advanced linear algebra. Most important is how to find the magnitude of a vector. Where is that? Over here. Magnitude is take the dot product with itself and square root it. Correlation coefficient is the cosine of the angle between two vectors. But from this formula, dot product formula, cosine theta is a dot b over length a, length b. And the other important review is how do you take dot products for functions? You multiply and integrate. Okay. Now we are going to do more things. We are going to find the correlation between two signals. So why is this important is remember we are going to modulate message signal and send it over a carrier. Some of the things we are learning here, the foundation is laid here, but we have to teach that foundation. There is no escaping that. But the real application will come in that 4th year course, digital communication. Because, for example, your mobile phone, it takes, when you speak, it takes your analog audio signal, amplifies it, convert it to digital signal. Then lots of math is happening, like lots of processing, like there is source coding, channel coding, things like that. And when you start learning that, one of the question is how dissimilar two signals are, or how similar two signals are, two message signals are. And it is you will be doing that in the digital domain, but the foundation is laid here. So we have to start thinking about, you have two waveform or two signals in the same domain. Are they similar or dissimilar? So we calculate the correlation coefficient. So I believe that is the next example. So the first one is correlation coefficient between two vectors in R3, which is easy. You calculate the dot product by going 1 times 2 is 2, 1 times 1 is 1, minus 1 times 1. That's what I did here. And magnitude is calculated in the usual way. So for vectors from R2, R3 or R4, calculating the correlation coefficient is straightforward. But in the next example, I am finding the correlation coefficient between two functions or two signals. So I have to do the dot product, which is multiply and integrate. And then I have to calculate the length of this signal and length of signal. How do you calculate the magnitude of the signal? You multiply by itself, integrate, but then take the square root. Multiply by itself, integrate, and then take the square root. And after you do all of this, you get this. By the way, these examples in the first lecture, some of these you may get in the first midterm, in your midterm exam. So please go through them and make sure you can do these integrations and remember the formulas. Of course, in this year or last year, it will be an open book exam, so you will have your formulas in front, but still it's good to understand. Okay, now there are more examples of functions considered as vectors. Show this is orthogonal to this. So this is okay. Hold on a second. Up to this point, do you guys have any questions? Is okay? Hello guys. All right, thank you. So this is the same thing. I don't want to really spend too much time, but something important is coming here. So cosine 2t is perpendicular to cosine 3t. So I multiplied and then I used that formula I showed you. Cosine a times cosine b is half cos a plus b. So it's 5t. Then a minus t, which is 2t minus 3 negative t. But cosine negative t is the same as cosine t. Then this is one full period. So cosine t is definitely 0. The top area cancels with the bottom area. But this is 5t. There are more top areas cancel with more bottom area. So this is 0. So it turns out as long as these numbers are integers and they are different, it is 0. And you may also want to see what happens. Don't try to. So in other words, as long as the numbers are different, the signals are perpendicular to each other, orthogonal. So cos 5t is perpendicular to cos 7t. Now cos t is not perpendicular to cos t. So if you multiply and integrate cos, it will become cos square, and go through that and see what number you get. But as long as the numbers are different, they are perpendicular. Another important thing is sin t is perpendicular to cos t. And this is left as an exercise. Again, you can put any number here. For example, sin 2t is perpendicular to cos 2t. And even if you change the numbers different, the dot product is going to be 0. So sine of anything is perpendicular to cosine of anything as long as you have integers there. And this is important in Fourier transforms because I am sure you learned this in signals and systems. So I think we are going to go there pretty soon. Okay, to talk about that, we have to review linear algebra where what is a basis for a vector space. So we usually write vectors in terms of a basis. We have ordinary bases and then basis where we have vectors that are perpendicular to each other. This is called the standard basis. For example, this is I and this is j. So we usually write the vectors in terms of I and j. For example, when we talk about the vector 5, 1, what we mean is it is 5i plus 1j. In other words, it is 5 times 1, 0 plus 1 times 0, 1. So this is the basis. This is not an ordinary basis. If you take the dot product, it is 0. So it is an orthogonal basis and it has a fancy name, standard basis. But for R2, there are other orthogonal bases. For example, if you remember this terminology, these two vectors are linearly independent. Therefore, they can work as a basis. But not only that, they are perpendicular because you can take the dot product and it is 0. So we can actually write the same vector 5, 1 in terms of these vectors. When we write that, I can't see this. It turns out 5, 1 is 3 times this plus 2 times this. I just guess these numbers, okay? You can actually write A here and B here and solve a linear system to find A and B. But in this case, it is easy to guess those numbers by trial and error. So the vector 5, 1, which is written in the standard basis notation, can also be written as 3, 2, with the understanding we are using a different basis. So these 3 and 2 are called the coordinates of this vector with respect to the new basis. What is the new basis? 1 and 1, 1 and I believe it is 1, negative 1. Yeah, 1, negative 1. So in general, if someone gives you a vector in the standard basis, you can find the representation of that vector in another basis, orthogonal basis, by solving a linear system. Actually, you can do this for any basis, not just orthogonal basis. But if it is an orthogonal basis, there is a faster way of finding these coefficients. What do I mean by the coefficient? The 5 and 2. Okay, and this is the formula. Okay, if this is your new basis vector, your vector can be written in terms of those vectors, and the coefficients is this. You take your new vector and dot it with the first basis vector and then divide it by its length. That would be the number sitting in front of B1. Take u and dot it with the second basis vector, dot it with that and divide by the length of it. That will be the second one, and so on. So this is where the Fourier transform business comes. Given a signal, when you expand it in terms of a Fourier series or Fourier transform. Let's first talk about Fourier series. The coefficients the Fourier coefficients are actually the dot product with the basis vectors. But because these are signals, dot product is written as an integral. So you get an integral at the top and integral at the bottom. But we have learned to calculate the integral at the bottom and we memorize it. And in the end, you get a single integral. Okay, so let's go to Fourier bases. So earlier I told you cosine kt and cosine lt is perpendicular as long as k and l are different and they are integers. Or here it is even more there. That theorem is even stronger. As long as they are integer multiples, it always works. They don't have to be integers themselves, but the relationship is integer multiples. So if you take this set, all these vectors are perpendicular to each other. So this is perpendicular to each other, this is perpendicular to each other, and this is perpendicular to, and so on. So in fact, this is an orthogonal basis for all functions with this period. Period has to be 1 over f0. If you change the period, then these numbers change. So I am actually summarizing you probably like 2 lectures or 2 lectures in signals and system. I don't know whether they explained it this way. They probably gave you a formula, but this set is orthogonal and it forms an orthogonal basis for all periodic signals of a particular period. And what is that period? It is 1 over f0. So that is what I am talking about here. And then because it is an orthogonal, because this is a basis, any periodic signal with this period can be written in terms of this. And when you do that, we call that Fourier series expansion. So if x of t is a periodic signal with period 1 over f0, we can write this as this infinite series. This is a constant and there are coefficients a1, a2, a3 and so on. And there is an n here and then bn sine n 2 pi f0. And you memorize the formulas for a0, an0, an and bn in signals and system. I just did a little bit more theoretical explanation. So let's look at an. An is the dot product of xt with cosine n 2 pi ft. See the dot product. And then in that formula, there is something at the bottom. This one. But that is the length of b1. We already know b1. So we can already calculate b1 and put it, just simplify it. And when we simplify it, it became, that's where this 2 over t0 came from. What was at the bottom came here. Of course, when we integrate this, we may got some constant too, but you may be wondering where is the bottom disappeared. It is sitting, part of this came from that. Similarly, bn is calculating by taking the dot product of your periodic signal with sine 2 pi f0. Okay, and the because the mean value of cosine and sine is 0, the mean value of xt is the same as a0. So a0 can be obtained by just integral. Oh, you can also think of this taking the dot product of xt with 1, because remember the first vector is 1. But it is also important to understand this is the mean value. Alright, so this is the trigonometric Fourier series. When do we use trigonometric Fourier series? When we have a periodic function. This is very important, periodic function. Okay, then I have this example. So I would like you to go through this, except one important qualification. So this is a periodic wave, height is 2 pi, the period is also 2 pi. A0 is easy, we calculate the average value. So I calculated only from 0 to 2 pi. Area of the triangle is half 2 pi times 2 pi, and then I divided by 2 pi. This is fine. Now, when you try to do this integral for an, you end up with t cos nt dt. Does anyone remember how to do this integral from first year? X cos x dx. X cos x dx. What method did we use? Hello guys. Does anyone remember how you integrated x e to the x? Okay, do you guys remember something called integration by parts? Okay, so that's the only way to do this integral, and the reason I am talking about this is I'm not going to ask you to do this in the exam. Okay, I'm not going to ask you to do integration by parts. If there is anything like this needed, I will give you the answer. Okay, you don't need to do integration by parts in this course. Alright, but remember that's the only way to do this integral. Okay, the same thing here, but this answer is a little bit important for your lab assignment. Okay, because look at what's happening here. By writing the Fourier series expansion of this triangular periodic wave, we are learning that triangular wave, periodic wave, can be written as a sum of an infinite number of sine waves of different frequency and different amplitude. So this is the fundamental. This is called the first harmonic, second harmonic, third harmonic, and so on. But it is important to see here, in general, the engineer Fourier, Joseph Fourier, actually proved any periodic wave can be written as a sum of sinusoids of various frequencies and sine waveforms and cosine waveforms, and their frequencies go in this pattern. If the fundamental frequency is f, then you will have 2f, 3f, 4f, and 5f. But depending on the shape of the signal, some of these coefficients may be 0. So, for example, if you take a different shape, it could be only sin t, 3t, and 5t, 7t, and so on. There are other shapes which have only the even harmonics, 2t, 4t, 6t, and so on. And the other thing is this triangular wave has only sine. There may be another shape that has only cosine, and there are other shapes which have both sine and cos. Okay, so this is called the Fourier series, and these numbers sitting in front are called the Fourier coefficients. Okay, Fourier coefficients are calculated by doing this integral. But where did the integral come from? Integral came from dot product. Okay, So when you have a periodic signal, we can plot these coefficients against the frequency. Okay, and when we do that, so we only plot the amplitude. Okay, by the way, I didn't have time to adjust. This arrow should be moved. Hold on, F0 is in this. Yeah, this is just, this diagram does not really corresponds to this. Okay, this is just an example. Let me repeat. And also this, I think I should have flipped it, but put it down, I forgot. But basically, if these numbers are, actually look at this. In this case, they are all negative except the first one. So I forgot to flip this. Okay, the arrow should be pointing upward. Please remember, arrow should be pointing upward. So when we have a plot like this, this is called the frequency spectrum. Okay, so the frequency spectrum of a periodic wave is discrete. It looks like at discrete points, and then you will have an amplitude. This is called the frequency spectrum. And later on you will see we go to something called exponential Fourier series. Then you will have the same numbers sitting on this side also. So we will have amplitudes for positive frequency and negative frequency. In general, this is called the frequency spectrum. So remember, very important point for the lab, if the original signal is periodic, you get a discrete frequency spectrum. This is not continuous. You will have amplitude sitting at different points, or spikes, or the delta functions. Okay, before we go to let me see how much we have to reach. Okay guys, so we have, hold on one second. We have only a little bit to go, so should we go without taking a break? Only like 4 more pages. Should we go without taking a break? All right, good. So before I talk about exponential Fourier series, I want to review the complex numbers a little bit. How do you write the complex numbers in polar form? So first you find the amplitude, you write it, magnitude of the complex number, which is by taking the square root, squaring, adding and taking the root, then e to the, we need an angle, and the angle is the polar angle of this. If you plot it in the Argand diagram, you put 3 here and 4 here, and you calculate the angle that vector makes with the x-axis, which is tan inverse the y number over x number. So it's always tan inverse over this number over this number. And what is this number? The square of this plus square of this, and then the square root. Okay. The other thing is how to take the dot product of the complex numbers. When you take the dot product of the complex numbers, you basically multiply the complex numbers, but we conjugate the second number. So Z2, 1 plus J2 becomes 1 minus J2. This is important. Okay. Dot product of the complex numbers is just the product. You just multiply, but you remember to conjugate this. And then you have to remember J square is negative 1. So this becomes plus 6 because J square is negative 1. All right. I think now you are ready to talk about. For periodic signal, we have another basis, orthogonal basis, and that basis has these. The vectors are e to the j 2 pi f0 t, e to the j 4 pi f0 t, e to the j 6 pi f0 t, and then the negative ones, the negative exponent, e to the minus j 2 pi f0 t, e to the minus j 4 pi f0 t, and so on. And then there is one at 0, e to the 0, which is 1. So 1 is always there. So basically the idea comes from, Earlier, we had a trigonometric Fourier series where everything is cosine or sine. But cosine and sine is connected to e to the j theta, if you remember to put the j here. And by rearranging this Euler's formula, cosine is equal to this and sine is equal to this. So you can take the trigonometric Fourier series, which we talked about before, and plug in these values. And then you will get, you can write, for example, let me go back here. This is just the idea. This is not how we calculate the exponential Fourier series coefficient, because there is another formula. But what I am saying is, for this sine t, you can write e to the t plus j, e to the something divided by something. The same thing here, and same thing here. So basically, you can substitute for cos and sine, and you have a formula like this for cos and then another formula for sine. But the most important thing is, this formula introduces negative frequencies. Okay, but because this negative should be interpreted as n2 pi negative f0t. So you have to understand negative frequencies are not real, but they are created by going to complex numbers. It's an artifact of the mathematics we are doing. Okay, all right. So basically, now we go back. The basis vectors are this. So you can write any periodic signal g of t in this format. N goes from negative infinity to plus infinity, including 0. So it is like negative million, then 100, 99, whatever, 0, and then 1, 2, 3, blah, blah. N is still an integer. Okay, and dn's are called the exponential Fourier transform coefficients. And the formula for here is this. Okay, this formula is slightly different from that, but it's once again a dot product. And this time the Fourier coefficients answers will be in general complex, but they can be written in the exponential form. And then this guy, the magnitude of this complex number, we plot that and we call it the amplitude spectrum. And because dn is a complex number, you can write it in the polar form. There will be an angle, and the angle is called the phase spectrum. Okay, so I have only given you the frequency spectrum. This is just an example. So you can see there is positive frequency and negative frequency because of the math. Okay, this is called the amplitude spectrum for the exponential Fourier series. If we are talking about trigonometric Fourier series, you have only the positive frequency. Okay, this I should have erased. There isn't anything. What is now? Okay. Finally, an orthogonal basis for any function. But we generally use this for aperiodic signals, because when we have periodic signals, we will use either trigonometric Fourier series or exponential Fourier series. When we have aperiodic signal, something that is not periodic, Joseph Fourier proved this set forms an orthogonal basis. What does this mean is, there are infinite number of vectors, but this infinity is different from the infinity we had before. In trigonometric Fourier series, the frequencies are 0, 1, 2, 3, and so on. OF, 2F, 1, then 0 frequency, which is a constant. Then we have F0, 2F0, 3F0, and so on. That is the infinity associated with integers. Do you guys know that there is a different definition of infinity other than what you studied in calculus, which is more to do with numbers, the new infinity, and the infinity regarding integers is different from the infinity regarding real numbers. In other words, there are more real numbers than integers, even though both are, there are infinite number of them. So Here, the frequency can be any real number. So in this set, you have e to the j 2 pi 1t, no problem. E to the j 2 pi 2t. But you also have e to the j 2 pi 1.5t. You have e to the j 2 pi 1.3t. You have e to the j 2 pi 1.77783t. So the frequencies are everywhere. So the important truth is, if you have a periodic signal, the Fourier representation has frequencies only at discrete points, f0, 2, f0, 3, f0, and some of them may be negative and some of them may be 0, but they only appear at discrete values, the multiples of the fundamental, the period or the frequency. But if this is an aperiodic signal, like take, erase this and erase this, have only one of these. In other words, your signal is always 0. It doesn't have to start at 0. So I will deliberately make it start at t0. So imagine the signal comes like this and stop 0 and then rises at t0, then falls back and to 0, and then thereafter it is always 0. So it is 0 and then rises, does some magic or flies around, then 0 again. That is an aperiodic signal. If you want to write this as a Fourier series expansion using trigonometric series or exponential Fourier series, the both sides, they would not be equal. You can't write it as a linear combination of sines and cosines where the frequencies are like integer multiples. You have to first, it is better to go to exponential first, but exponential Fourier series won't work, because in exponential Fourier series, again, you have integer multiples. There is that example. Yeah, this is an example here, right here. N goes from negative infinity to plus infinity, but then n is an integer here. You have e to the j 1 2 pi f0 t, then e to the j2 2 pi f0 t 3, and then negative 1 negative 2 negative 3. But to write an aperiodic signal, we need frequencies at every real value, which means the spectrum of an aperiodic signal will be, in general, continuous. It is not discrete. Every frequency is there. So, but before I show you this, the formula, this is the most famous formula for Fourier transform you have here. So, G of t is a signal, time domain representation, its frequency domain representation, or the Fourier transform is in general denoted by capital G at f. You guys know this notation. But how do you calculate it? Negative into plus g of t e to the minus j to the dot product here. Okay. And the vectors are in your orthogonal set is e to the j2 pi ft. Here you have e to the minus j2 pi ft. Why do we have this? Because when you take the dot product of complex numbers, we conjugate the second one. That's why the plus j became minus j. Okay. So the frequency spectrum in general is continuous. Okay, does this make sense? Please remember this because this is important for one of the post labs. All right. Okay. Now, something very important, and this is very strange. Every time in this course, in the midterms, we ask the students, like, remember in those years it will be written part before the pandemic. By the way, the last two terms, the midterms and the finals, were short answer questions or multiple choice. This time I have less number of students, so you guys need to write your midterm in the written part. Okay, you have to write your solutions on a piece of paper and upload it to D12. It won't be like an online exam. Okay, I will post a PDF. You have to do a written exam because there are only a small number of students, so I'm going to correct. So anyway, whenever in the middle of amplitude modulation analysis, the first part says calculate the Fourier transform of something, people started using this formula, which is the fundamental way, calculating the Fourier transform from the first principle. But you do that in signals and system in like one lecture. After that, you learn to calculate the Fourier transform from the table. And it looks like students have passed signals and system, but they don't know how to use this table. So this is very important. Okay. So in the next lecture, I will show you some example how to use the periodic table, Fourier transform table. And also your TAs will do some questions. So they are very important. Okay. Because if your skills and knowledge are only up to like getting an A plus in signals and system, getting an A plus in signals and systems means nothing. Okay, because you don't really learn signals and system properly in that course, unfortunately, and it's very hard to change. Okay, because if you guys learn properly, then why is every time we ask you to calculate Fourier transform, people write the definition? Okay, and it will take a long time to calculate the Fourier transform. So, for example, what I am trying to tell you is this. What is the Fourier transform of cosine 400 pi t? 400 pi t. So 400 pi t means f0 is 200. So it is 2 delta function at 200 and negative 200. So, and also I want you to visualize this. You should visualize 2 spikes or delta function here and here. Okay, that is for cosine. So do you guys see this is a periodic waveform? So your frequency spectrum is discrete. Okay. And then the rectangular function, for example, what is the Fourier transform of the rectangular pulse? A periodic pulse, t over 10. That means the width is 10. So here it is a sinc function, which is particularly 10 sinc pi f10. I'll go over those things in the next lecture. And that's not enough. You need to do how to do frequency shift, time shifting and frequency shifting. In other words, if the Fourier transform of g of t is capital G of, what is the Fourier transform of g of t minus 2? It will be the same Fourier transform you get here multiplied by e to the j 2 pi f2. Because t0 is 2. If t0 is 3, then you will put t0 here. And how do you do these things very fast? Did you guys do a lot of exercises like this in signals and systems? Signals and systems? Oh no. Hello guys. Don't be shy. Did you guys did? Then why are students still going to find the thing they write there? For example, I remember last winter, not this winter, before the pandemic, in the midterm, students need to find the Fourier transform of a square waveform. And we taught them how to do it using methods like the way I described, but in the exam, half the students wrote the definition and tried to integrate this and then got lost halfway through. So what happened? All right, anyway. Okay, guys. So we will continue on Wednesday. Please come at like 9:55 and wait, because I will start the lectures exactly at 10 o'clock because we have only 2 hours, right? So, we will try to use the same Zoom link, and I don't know if Zoom is going to have any problem because everyone is late 1 hour. I don't think it should be. If that's the case, please check your emails. If you can't log in next time on Wednesday at 10 o'clock, please check your email. I will send you a new link. Oh, not the email. I'll post the link on D2L. Okay. If you can't log in, go to the D2L and see. I would have posted a new link for 10 o'clock, 10 to 12. Okay, guys. By the way, another important thing. It's better to tell. You know what? We'll talk about that the next lecture. Okay. By the way, if you like, you can read ahead the notes for the next few lectures. For example, next lecture, and ask me more questions in the lecture. I like you to interrupt me and ask me questions during the lecture, okay? Rather than waiting until the last when I finish the lecture. All right, guys. Okay. Do you guys have any questions? All of this is good. Okay. All right. Thank you, guys. So I'll see you guys on Wednesday at 10 o'clock.